Ever wondered how AI models like GPT or BERT understand language so profoundly? The answer lies in a revolutionary architecture called the transformer. Today, we're diving deep into the mechanics of transformers, exploring how they process information, the math behind their attention mechanisms, and why they've become the backbone of modern AI. Let's break it down. Before transformers, sequence models like RNNs and LSTMs struggled with long-range dependencies. They processed text sequentially, which limited speed and efficiency. Imagine trying to read a book one word at a time, slow, error-prone, and impossible for complex tasks. Transformers flipped this paradigm by enabling parallel processing, allowing models to analyze entire sequences at once. This leap wasn't just about speed. It was about capturing nuanced relationships between words, no matter their position in a sentence. At the heart of transformers is the self-attention mechanism. Think of it as the model's ability to focus on relevant parts of a sentence dynamically. Here's how it works. Each word in a sequence is transformed into three vectors, queries Q, keys K, and values V. The model calculates how related each word is to every other word by taking the dot product of Q and K, scaling it, and applying softmax to get attention weights. These weights determine how much each value contributes to the final representation. Mathematically, this is expressed as attention QKV equals softmax, QKT slash square root DKV. Where DK is the dimension of K, this allows the model to weigh the importance of different words contextually, not just sequentially. But wait, how does a transformer know the order of words if it processes them in parallel? Enter positional encodings. These are fixed vectors added to token embeddings, encoding each word's position in the sequence. They use sine and cosine functions of different frequencies, ensuring the model can learn relative positions. For example, the positional encoding for position I and dimension D is Pi2k equals sin I slash 10,000 2k slash D. Pi2k plus 1 equals cos I slash 10,000 2k slash D. This clever trick lets the model infer relationships like the cat is on the mat versus the mat is on the cat by capturing positional differences. Transformers use an encoder-decoder structure. The encoder processes input text, generating contextualized representations, while the decoder generates output step by step. Each has multiple layers of self-attention and feed-forward networks. For example, in machine translation, the encoder analyzes the source sentence, and the decoder builds the target sentence, using cross-attention to align relevant parts. This design enables tasks from translation to text generation with remarkable flexibility. Modern models like BERT and GPT leverage transformers at scale. BERT uses a bidirectional encoder, masking tokens during pre-training to learn context from both directions. GPT, on the other hand, employs a unidirectional decoder, excelling in generation tasks. Their success hinges on massive datasets and parameter counts, but even smaller variants like distill BERT demonstrate that efficiency can coexist with performance through techniques like knowledge distillation. Transformers aren't just a technical achievement, they're a paradigm shift. By prioritizing relationships over order and enabling parallel computation, they've unlocked new frontiers in NLP. As research pushes further, we're seeing innovations like sparse attention, efficient architectures, and multimodal models. The next time you interact with AI, remember, it's the transformer, not the old-school RNN, that's doing the heavy lifting. Thanks for watching, stay curious, and keep exploring the science behind the magic. Like this video. Subscribe for more deep dives into AI research. Want to see how transformers handle code or images? Let me know in the comments. Until next time.